Welcome back. Newton's first law of motion. An object in motion stays in motion. An object at rest stays at rest unless acted upon by an unbalanced force. So it says an object at rest, which is not moving, will stay at rest, not moving, unless acted upon by an unbalanced force. An object in motion will continue that same motion unless acted upon by an unbalanced force. So something that's moving would just keep moving in a straight line forever unless there's some unbalanced force. We said typically on Earth that unbalanced force is friction, so it's always slowing stuff down. Okay, but like in space, when we looked at that little example, that satellite is just going to keep going in a straight line forever unless there's some unbalanced force that acts upon it, or like the guy who was skiing, sliding down a hill in the movie. Okay, his motion continued in the same direction because it was, he put that stuff on the sled so there was no friction, and he would continue in the same direction until he was finally acted upon by an unbalanced force. An example of Newton's first law, okay, the Earth's orbit around the sun, it'll keep moving fast, it'll keep moving forever around the sun unless acted upon by an unbalanced force. Or a book sitting on a desk will not just start moving on its own. Inertia is the tendency of an object to doing what it's already doing. If the object is not moving, inertia resists it to start moving. If the object is moving, its inertia resists it stopping or changing the motion. Okay, so it's just really a measure of the first law. Okay, and we said inertia depends on mass. Okay, and we looked at some exaggerated things with trains. It's got a huge mass, so you can really see they have just a tremendous amount of inertia. Why is Newton's first law called the law of inertia? Okay, inertia is the measure of the amount of force it will take to overcome a change in motion. The first law says that things don't move on their own, and things that are moving don't just stop on their own. Inertia is a measure of that tendency. Inertia is called momentum. When an object is moving, it's equal to the mass of the object times its speed. So there is an equation for momentum that we don't get into too much. The equation is P, which is the variable they use for momentum, times it equals the mass times the velocity of the object. Okay, Newton's second and third law. Okay, this law connects force, mass, and acceleration together in the equation. Force equals mass times acceleration. So there it is, F equals m times a. Okay. Now, whenever you see this blank triangle, okay, we need to be able to put variables into the triangle. So it really says F equals m times a. Okay, when the variables are next to each other like this, it means multiply. So any equation that you see that we use this year with 3 variables, you can get over here into this triangle to make sure you do the math right. So we have m times a, and that's what we put in the bottom of the triangle, are the variables that are multiplied together. So we're going to put the m and the a there. And the third variable goes in the box that's left. Okay. So it says objects will have a greater acceleration if a greater force is applied. This is common sense. If you want to hit a home run, you hit the ball hard. If you want to hit the punt, okay, you don't hit the ball very hard. So the baseball will have a greater acceleration if you hit it harder. More push or pull means it changes its speed faster, it changes its velocity faster, and accelerates more. The other thing it depends on is the object's mass. Mass and force applied affect motion. More mass means less acceleration, and less mass means more acceleration. So for example, if you had 2 balls and they had different masses, one of them was really, really heavy and one of them wasn't as heavy, like the difference between like a tennis ball and a baseball. The tennis ball has a lot less mass. If you hit it with the same force as a baseball, tennis ball is going to accelerate more. There's a short clip that we're going to take a look at here on Newton's second law of motion.
Now,
Okay, now the second law of motion says that the acceleration of an object depends on two things. It depends on force and mass. So with this kid and the bat is going to provide the force, and to provide the acceleration, they're going to use a softball, and then they're going to use a shot put. A shot put is, if you've never seen one, it's just a great big steel ball. It looks kind of like a cannonball.
Let's look at Newton's second law of motion. This law describes what happens to a moving object when a force is applied to it. This batter will strike the pitched ball and change the ball's direction. He will try to strike the ball and change its direction. Well, if he does make contact with the ball, the force of his swing and the bat that he is holding will accelerate the ball in a different direction. There, the ball is hit.
Okay, so the acceleration of the ball depended on the mass of the ball and the force. The bat provided the force, and then there was the mass of the ball. So when he hit the ball didn't have a large mass with that force, the ball took off and it had a lot of acceleration.
It travels in the direction in which the force is applied. If the batter hits it straight on, the ball will change direction and travel in the direction of the swing. How much it accelerates depends on the strength of the force and the mass of the ball. Mass.
Let's review of mass and weight. Okay, mass is the amount of matter in an object. Weight is a measure of the force of gravity.
Is not the same as an object's weight. Weight is a measure of gravitational pull, and it changes as an object gets farther from the Earth. Mass doesn't change. It is a measure of an object's inertia. The greater the mass, the harder it is to get the object to start or stop moving. As we add more mass to this cart, the amount of force required to get the cart going increases. Newton found that the higher the mass of an object, the greater the force must be to change the object's motion. That's why we don't play softball with a shot put.
Okay, so same force, the ball has a much larger mass, so there was very little acceleration. The two things we said in the notes that acceleration depends on is mass and force. Okay, the force was the same, but in this case, it was this great big steel ball that had mass, so there wasn't much acceleration.
There would never be a home run, and bean balls would be lethal. So, the second law of motion says that the change of motion of an object depends on the size of the force and the mass of the object. The greater the force, the greater the resulting acceleration. The greater the mass, the smaller the resulting acceleration. It is harder to stop a train than it is to stop a car, even when the car is moving faster. That's because the train has a greater mass than the car and will require a greater force to slow it down. We say the train has greater momentum. Momentum is the strength of an object's motion. The more mass an object has, the greater its momentum. Momentum is determined by multiplying the mass of a moving object by its speed. The faster an object travels, the greater its momentum.
Solving for force. Okay, so we got, in the last little segment, we got the variables put into this triangle, and now we're going to use the triangle to solve some example problems. So calculating force, mass, and acceleration when you have two of the three parts of the equation. First thing in any word problem you should do is always identify what the question is asking. You can't answer unless you know what the question is. You fill in the parts of the triangle that you know, and then you use triangle to help you do the math. So it helps you decide, should I multiply? Should I divide? And if I divide, what should I be dividing? Which number should I divide which number by? Okay, so we're going to get the equation into the triangle like we looked at on the last page. M times A, force is at the top. Force is measured in newtons. Acceleration is meters per second squared. And mass is measured in kilograms or grams. Okay, so let's look at an example problem. What force is necessary to accelerate a 10 kilogram ball 500 meters per second squared? Okay. When you read, what is the force? That's the question. That's what they're asking you to solve for. So you can put a question mark where the F is in the triangle. We're going to put a question mark on top. Then it says we have 10 kilogram ball. 10 kilograms is mass. So we're going to put 10 kilograms where the mass is in the triangle. And the next number we read was 500 meters per second squared. 500 meters per second squared is acceleration. It says to accelerate, and then it tells us about the ball, a 10 kilogram ball at, and this is the acceleration, accelerate at 500 meters per second squared. So we're going to put 500 meters per second squared where the A is in the triangle. Now the numbers are on the bottom next to each other, so we know we're going to multiply. So when we go to solve the problem, okay, it looks like this. F equals, and then what's in the M box times what's in the A box. So it'd be 10 kilograms times 500 meters per second squared. Okay, 10 times 500 is 5,000, and the unit for force is newtons. Okay, so we solved for the top variable, which was force, okay, and we're going to kind of go around the triangle and solve for each one of the three variables. So this one says, what is the acceleration? So in the last problem we solved for force. This time we're going to solve for acceleration. Mr. Coleman, if Mr. Lenow used a force of 100 newtons to throw him, Mr. Coleman has a teeny tiny mass of only 5 kilograms. So what is the acceleration? That's the question. So we're going to put a question mark where the A is in the triangle. So we're going to put our question mark right there. And then it says Mr. Coleman has a mass of 5 kilograms. So 5 kilograms is mass, and we're going to put that 5 kilograms where the M is in the triangle. And then it says Mr. Lenow used a force of 100 newtons. 100 newtons is force, so we're going to put the 100 newtons where the F is in the triangle. Okay. The numbers are up and down, or top and bottom, so we're going to divide. So we're going to have 100 divided by 5. Okay, so it's literally this same fraction bar here, 100 divided by 5. If we want to write it out over here, it's 100 newtons divided by 5 kilograms. So the acceleration, 100 divided by 5, equals 20, and the unit for acceleration is meters per second squared. Okay, so now we did a problem where we solved for force, we did one where we solved for acceleration. So this one, we're going to solve for mass. What was Mr. Lenow's mass? Mr. Coleman used 20,000 newtons to throw Mr. Lenow with an acceleration of 400 meters per second squared. Okay, so we get our variables over here in the triangle. Okay. What was Mr. Lenow's mass is the question. So we're going to put a question mark where the M is in the triangle. That's what they're asking us to solve for. Okay. And then it says Mr. Coleman used 20,000 newtons to throw Mr. Lenow. So 20,000 newtons is force. So we're going to stick that where the F is in the triangle. So we're going to put our 20,000 newtons where the F is in the triangle. And then it says he had an acceleration of 400 meters per second squared. So that's our acceleration. So we're going to put 400 meters per second squared where the A is in the triangle. The numbers are top and bottom. So you're going to divide. You're going to divide the top divided by the bottom. This is just like a fraction bar. So our mass equals 20,000 newtons divided by 400 meters per second squared. So the mass equals 50 kilograms. Okay. 20,000 divided by 400 is 50. You're going to do some of these problems on your own, and then we're going to pick up here next time.